video, we're going to talk about continuous functions and parent graphs that we can use to determine a continuous function on an interval and determine domain and range about those continuous functions. A function is continuous on an interval if it is continuous at every point of the interval. So the important part here is we talk about how it's continuous on an interval. And that's very important because we can actually restrict and piece up that interval to make it continuous. So a continuous function is a function that is continuous everywhere on its domain. And so again, this is where it becomes important to recognize what the domain is, because some functions might appear discontinuous, however, they're continuous on their domain. So in example 3, we're going to identify continuous functions. So the first graph we're going to look at is y equals 1 over x. So this is actually a continuous function. And the reason it's continuous is because the domain of this graph is all x values such that x does not equal 0. So this is a continuous function. However, we do have a point of discontinuity. And for short, from now on, I'm going to call these PODs. And the point of discontinuity here is x equals 0. So yes, I do agree that there's a vertical asymptote right here at x equals 0, which creates a point of discontinuity, but because the domain does not include 0, the point of discontinuity is not in the domain, and therefore it is a continuous function on its domain. So now let's look at some other graphs. We're going to look at x squared and x cubed. Typically, we refer to these kind of graphs as polynomials. Polynomials do not have fractional exponents. They do not have fractions really in them whatsoever. They can have fraction coefficients, but you don't have like x squared plus 1 divided by x plus 1. So the domain for all polynomial functions is x such that x exists in all the real numbers. So all polynomials are continuous. They do not have any points of discontinuity because polynomials are always continuous everywhere. And so we can actually generalize this to say all polynomials are continuous with no points of discontinuities. All right, let's move on to our next function, which is the absolute value of x function. This is very similar to a polynomial function. And the domain of this is x such that x exists in all the real numbers. And again, we don't have any points of discontinuities. Now let's look at the exponential function. Again, the domain is x such that x exists in all the real numbers. We don't have any points of discontinuity here either. And the last function I want to look at is the logarithmic function. So this one is a little bit different because the domain of this is x such that x is strictly greater than 0. Because the domain for this is you cannot plug in 0 or a negative number into a logarithm. But again, on its domain, we have no points of discontinuity. And we have one more, which is the square root of x. So the domain for the square root of x is similar to logarithms, except that we can actually include 0 this time. So it's x is greater than or equal to 0. I want to make the note to say that all radical functions are continuous. So I want to make the point to say that all rational functions are continuous everywhere on their domains. They have points of discontinuity wherever the denominator equals 0. This is also true for trig functions. So for example, tangent or cotangent, secant or cosecant, where you can have them be undefined. Those would create points of discontinuities.